Hello dear, good morning, and you have started watching a video lecture on support vector machine, and today we are going to discuss the Kernel method, and in that context Kernel trick. What trick we are going to do and what way it is going to benefit us. So as you know that we have discussed in my earlier lecture that support vector machine can be deployed in a higher dimensional feature space where samples are linearly separable. And another hypothesis, and can be proved by Mercer theorem, that using Mercer theorem you can always design a kernel in a higher dimensional feature space, infinitely large it could be the dimension, where the samples could be linearly separable. So nothing to be worried about that. We could always find a kernel function in a large dimensional feature space. And now by this time you know the meaning of dimension. Physical dimension and the representational dimension, they are different, and we are talking here about representational dimension. So it turns out that this kind of picture, if you have pictorial representation, then perhaps things will be clear. So this is a phi which is called the mapping function, which is operating on these samples and taking these samples to a higher dimensional feature space. As you can see here, they are linearly separable, and I will try to demonstrate with a with an example, small example of few samples which are non-linearly separable in actual dimension where it is given, but applying phi will make it linearly separable. Then we can apply the support vector machine principle which we have studied so far, and it turns out that my Lagrangian function will just, because now you see with phi x with phi has taken the shape of phi of x, and now this earlier it was actually S I dot Sj, those are support vectors, dot product between the samples and the support vector, and it turns out this could be replaced by this, that is the mapping function. Everything remains same. Let us try to further clarify the very simple but elegant concept, by doing a problem by hand. Say we have taken samples 1, 2, 3, 4. 4 samples. They belong to 4 samples. They belong to positive class, and this 4 sample belongs to negative class. And if I just draw them, because they are very simple problem, I am doing it by hand. So only 4 samples are there, and 2-dimensional feature space x1, x2, and I told you that this is same. Don't confuse. We earlier talked about SI. Just so they are same. Sample. Sample feature. So these are the sample in the 2-dimensional feature space. And you know, this is what our constraint is. Constraint for the samples on the garter. That means for support vector. Now you see clearly this problem is non-separable in this plane, isn't it? Linearly not separable. Non-linearly, yes. Linearly not separable. So can we do something that this non-linearly separable problem, with a very simple example I am giving, by some kind of transformation can we translate it in the form of a linearly separable problem? Let's see. So these are my two sample sets. I have plotted them and they look like this. Okay, this is your negative class, this and this red one are positive class. Okay. Okay. Now let us define a nonlinear mapping function phi. Okay, Si 2D. Okay, so here don't confuse with the notation, they are very simple. Sample, that's why I thought that S will be good symbol. And what the nature of the function is 6 minus the sample plus sample 2 plus this is plus mod of sample 1 minus sample 2 if sample 1 plus sample 2, sample 1 square plus sample 2 square greater than 3. So this is the definition of the function which I have created, say, okay, for transforming the samples into a linearly separable problem. Okay, and then if it is less than 3, that means otherwise whatever, okay, if it is not greater than 3, then the samples remain as it is. Okay, so using this mapping function, can I transform the samples? Let us see one by one. Sample 1, 3, 3. Okay, then 3, 3 will remain. You see, first of all, you see 3, 3 is greater than. Will it be operated by this regime or by this regime? Okay, so by this regime. Why? Because you see 3 square plus 3 square, 9 plus 9, 18. 18 root over of 18 is greater than 3. So it has to be operated by this as per my definition, as per my Vim. Okay. So you see 6 minus the sample, you see 2 x1 x2. Okay, this is s1 s2. So that means 3. 6 minus 3 plus s2 minus s2 s1 minus s2, which is 0 here because 3 minus 3. So after transformation, the samples, you see, similarly you do this, okay, and sample remains at 3, 3. How about sample 2? 3 minus 3. 3 minus 3, you see, 6 minus 3 plus 3, because 3 minus 3, minus plus, so for sample 2 it is 12, okay, 12, 12. Okay. Similarly for sample 3, is it clear? I think you are you getting my point? You do it by hand. So this is S1, this is S2, this is S1, S2, this is S2, S1. So, and any sample, this is S1, S2, S1, S2 for sample 2. Okay, sample 1, 2, 3, 4, 1, 2, 3, 4. Okay, so that's how we are calculating. So 12, 12, sample 3 it is 15, 15, sample 4, 9, 15. So with a pen and paper you can do this with me. So we have transformed all these 4 samples into new form. Those are now 3, 3, 12, 12, 15, 15, 9, 15. Clear? Now for negative class, sample 1 again, okay, sample 2, sample 3, sample 4, they remain as it is. Why? Because you see S1 square is 4 plus 4, 8, root over of 8 less than 3. So this will apply for them. This will apply. Okay. Okay. So that's the reason they remains where they were. Now let's see what we have achieved. So just by applying this mapping function phi to all the samples of two category, now the samples can be plotted. So this is negative class samples remain where they were, and all the positive class samples, but they are not on scale, of course, because the space. So they are spreaded. You see, now they are not like this. They have been separated. Okay. And now suppose again here visually it is a tiny problem. So visually we can see we have a support vector from this negative class. We have another support, two support vectors are there. Okay, one from positive class, one from negative class. Now we can apply this. Okay, this one we can apply with y. Y is +1 -1 for different class. So just alpha, just we did earlier. Now it is a problem, simple problem, right? Now I have sample of which are linearly separable. So the hand problem which I did earlier, same thing I am repeating here. Alpha 1, this is plus alpha 2, this is equal to, this belongs to positive class and this belongs to negative class. I have fortunately only one support vector per class. So just dot product, if you do 3, 3, 9, 9, 9, 18 plus 1. So 1 again, to accommodate bias B, we have tactfully inserted B here. This is exactly same as what we did earlier. So this is a equation, linear equation in alpha 1, alpha 2. So two support vector giving me two equation. I can solve alpha 1 -8, alpha 2 11.67. Okay. And the moment I got that alpha values, then W curly I have written, because within this that bias is hidden, is alpha I, alpha sub I, S curly I, Y I. So you are getting simple alpha 1, alpha 2. After getting that, you can calculate W like this, and which is turns out to be minus 0.66, minus 0.66, 3.67, and then you can draw the decision boundary W1x1 plus, because the parameters are now known to you. Okay, this is W1, this is W2, this is bias B. So you have a decision boundary. But don't be afraid that you have, oh my god, you have got an alpha which is negative, and I told that alpha for support vectors will be always non-zero, will be greater than 0, right? Alpha will be greater than 0. This is KKT's complementarity condition. So this is because there actually this is hidden over here. This is not the alpha, this is yi alpha 1. Okay, that's why this belongs to negative class, this belongs to positive class, because I have already used this without simplifying this equation. Okay, so this alpha is actually with level. Okay, so alpha is positive 8, okay, with level it is -8. Anyway, we have understood, I believe. So you have got a decision boundary here. Here earlier also same thing. Okay, minus alpha, you should not be afraid, because this is actually with level. Now the decision boundary you have obtained. Now say somebody is giving you another sample for predicting. So you can still use this, because that sample has to be again mapped to the same feature space, okay, to test it, to predict it. You can do that. Okay, so this is one issue, that in the same dimension where all the training samples are there, and you have translated the problem into linearly separable problem, there itself you can take all the samples to be predicted having the same phi transformation and test it in which class it belongs. Also there is another way, but this is why people will do that. But sometimes if required with phi inverse, this is what in the higher dimensional feature space, which is linear, okay, straight line. But making inverse of phi, you can again bring it back to the original domain, and there the decision boundary will be like this. Okay, so oops. Okay, so this will take the shape, the straight line will take the shape of this curve in the actual feature space from where you transfer the data. Is it clear? So that is wonderful, right? So you have samples which are linearly not separable. So you have designed a mapping function, okay, and took it in the in a nonlinear mapping function you have taken, and then you have taken the samples in a different space, and there it is linearly separable, and as it is you are applying the support vector machine training principle there, and predicting also from there is possible. But if you want to come back to the original domain, then of course the decision boundary will take this shape, okay, because inverse phi mapping will take that shape into this shape. That's it. Then what is the problem? It's a deep problem, because great problem is there, because this is simple toy problem, okay, and somebody has devised the mapping function like this and it worked. So for in general, designing this mapping function is very cumbersome, okay, and that's why we need to make some trick, which is known as kernel trick. So what is the trick we will do? I am going to tell you now. Okay. So the trick which we are doing here, now say this is a kernel function. Now again the notation, okay, j here is in vector from x and z, okay. So that means you have sample from different levels or different classes. There one class x, another class z, okay, in vector form they represent. I believe this is clear. Now you see the trick which we are making here, forcibly I am telling, okay, I know a kernel function k, which is xz, okay, which will work on xz, and that will be equal to the dot product between the mapping function which I do not know. Okay, and then it turns out that there are some general kernel function which will always work in place of this, which is very cumbersome or difficult to figure out. I will illustrate this concept with an example. Say I have this mapping function phi x, 2 dimension, small example I have taken is x1, x2, okay, and this phi z is actually 2 dimensional z1 phi of z1 z2, and this mapping is such, so this is I am taking to a feature space where I decide all combinations of this x1 into x1, x1 into x2, then x2 into x1, x2 into x2. So it was 2 dimension, now the feature space become 1, 2, 3, 4 dimension, 2 cross 1. So this is actually you are taking to higher dimension. You can make it further higher, we will discuss that, okay. So the example is clear, right? So whimsically I have just taken all the combinations of this. Then I have told forcibly with some trick, I am making this is equals to this. So what is this? This is equals to the dot product between the this samples mapped by phi x and the samples mapped by phi z. So if you do the dot product, then what are you getting? You are getting x1 z1 square plus x1 x2 z1 z2 plus x1 x2 z1 z2, that is 2x1 x2 z1 z2 plus x2 z2 square, that is eventually x1 z1 plus x2 z2 whole square. What is it? This is nothing but dot product before this transformation in this ugly higher dimensional feature space in the original space. You see? So this is the trick. Okay. So this is a kernel, and you see, it is called quadratic kernel. Making this 2, 3, 4, 5, I can represent any ugly phi x dot phi z. I will explain that. And this is the trick. You see, whatever you do in higher dimensional space, that is equivalent to in the original dimension, but with a polynomial index. That I have proved here with very small example. Same thing you can do it. Suppose now my problem is such, I decide I will take it in 3-dimensional feature space x1, x2, x3, and then with phi, that is mapping function working on 3 dimension, will be equals to suppose x1 cube root 3 these. So all combination, and this is I decide. Okay, phi z also is like this. Okay, so again this turns out to be that using kernel trick, this is nothing but the cubic polynomial. So in original domain, you are just doing this, okay, x1 z1 plus x2 z2 cube. Similarly, you can just make any ugly mapping function of your choice, okay, and I will be able to reduce it to a simple trick of polynomial kernel. Okay, so this is called trick. I am getting the benefit of taking my data, applying some very complicated mapping function, taking it to a higher dimensional feature space is same as selecting some kernel. This is incidentally both the examples I gave you with the help of polynomial kernel, sometimes quadratic, sometimes cubic. In general, it is called polynomial kernel. So we have we can get the same benefit of taking the data in a higher dimension to the kernel function, which is a polynomial function. So this is the trick. Isn't it a great trick? You are not going to higher dimension actually, but you are taking the fruit of as if taking the data to a higher dimensional feature space where they are linearly separable. Okay. So now with this trick, you can guarantee that the data will be linearly separable if you apply a non-linearly separable data, if you apply a polynomial kernel, that is transformation you are doing using this. Okay. So x dot g plus 1 is in general form, d is the degree of polynomial. Okay. Then we have many researchers have researched, and for different class of problems, they have figured out different types of kernel function. One such kernel function is Gaussian kernel function, which is defined like this. Okay, e to the power minus x minus z square 2 sigma square. Okay, so you have the sample, so you know all the samples can be now transformed using Gaussian kernel. Okay, so and you can guarantee that they will be linearly separable. Isn't it great? Similarly, you have Gaussian radial basis function RBF, simply just making this as a parameter gamma. So here gamma is essentially 1 by 2 sigma square is a particular case. Gaussian kernel is a particular case of Gaussian radial basis function kernel. This is very popular kernel, RBF kernel. Okay, so they can help you to take your data to a infinitely large higher dimensional space where they will be linearly separable, where you can apply support vector machine. Okay, Laplace RBF kernel, you have similar to this, but instead of 2. So people have worked, they have published paper, research, and designed some kernel for a class of data which you are trying to classify. Similarly, we have hyperbolic tangent kernel, or sometimes called sigmoid kernel. 2 parameters are there, beta naught, beta 1. Otherwise, they are tan hyperbolic of x dot j. So, you see, once I have labeled sample, I can pass through any of the kernels. Now, which kernel, of course, we will have to decide. It depends on the problem. Okay, understanding of your problem that I have non-linearly separable samples. Now, which kernel to use? So, from the trick, you know that you have some standard kernel, okay, and they will do your job. Believe me, they will. You don't require any more of that phi, which by hand in doing I have these minus some, these all kind of thing, right? We did. So you don't require actually, but the intention of doing that was to take your sample to a dimension where they are linearly separable. That will be fulfilled if you use any of the standard kernel functions. Of course, for some samples, the nature of the samples, depending on the nature of the samples, you will have to choose judiciously your kernel, and the efficiency of your sort vector machine will depend to some extent to that. So this is called kernel trick. We don't require phi anymore. Any of this standard kernel will do the same job.